This is part 1 of lecture 5, and the overall topic is bonding and nomenclature. And I'm going to start by simply introducing the two types of bonds we're primarily going to discuss this semester. So let's share. Share. All right. So we're talking about chemical compounds, chemical molecules. Remember, a molecule is two or more atoms bonded together chemically. Does not matter if they're the same or different. Compounds, however, are two or more different atoms. And the primary types we're going to learn about this semester are ionic bonds and covalent bonds. Here's your covalent bond. A covalent bond involves the sharing of electrons between atoms, whereas ionic bonds do not share electrons. Covalent bonds involves a sharing of electrons between atoms. Ionic bonds do not involve the sharing of electrons. That attraction is more of an electrostatic, of a positive and negative charge. They're both very strong for different reasons. Okay. So I like this visual. If you remember last hello brain lecture, I talked about, or last class, some of the definitions we use. So we have an element encompasses either a single atom or it can be joined together chemically. They're still elements. A molecule is two or more atoms chemically bonded. It can be also called an element, so you have the overlap here. And within there we get the subset called compounds, which is two or more different elements chemically bonded. So these are both molecules. This is not a compound because they're the same. This is a compound. So this is just a good visual for separating out those definitions. And I talked about I talked about making ions. Why does an element become an ion? It wants a fold shell. It wants this designation right here. Your noble gases, your group 8, have all paired electrons. They have filled shells. Remember, a shell, period 1, only has 2 electrons because it's just hydrogen and helium. But all the others have 8. So neon has 8 valence electrons. Valence are your outer shell. So it has a total of 10. It has the 2, and then the next level out, it has 8 more. Argon has a next level out. It has its third orbit, its third shell, but it's also 8. It's filled. Each one of its electrons is paired, and that is what an atom wants. That's the lowest energy state. When it reaches this configuration, it says, I'm good, thank you very much, I'm going nowhere. So fluorine only needs 1 electron, right, to become a filled shell. So that's what fluorine is going to do. It's going to take an electron from somewhere, and now it has a full shell, and it is a fluoride ion. Remember, IDE ending for anions. Nothing special for cations. So it's going to be the fluoride ion or fluoride anion. They're both correct. And it will have a -1 charge because it gained 1 electron. And it now has 1 more electron than proton. So that imbalance is what the charge designates. We go over here to magnesium, same thing with calcium. They have 2 unshared electrons. So the quickest way to go to the noble gas configuration, and in this case, these guys are going to go to the configuration of the previous period, that inner shell. That's okay. It's going to lose electrons. Now, right, magnesium is on period 3. its electron configuration is going to be the same as the noble gas for period 2, because when it loses the 2, there's nothing left on the period 3. It's still filled. That's what it wants. So it's got a neon gas configuration or neon atom. And it has a 2+ ion, magnesium ion or magnesium cation, has a 2+ charge because it's given up 2 electrons to get to this configuration. So ions are generally exist in that state, or often are stable in that state. So they are in nature as ions very often. So ions will make ionic bonds. That makes sense, doesn't it? And an ionic bond is going to be between a negative charge, so that's one of these guys. Remember, these are the nonmetals, aren't they? So something from this column or this section of the periodic table, which happens to be nonmetals, these are going to be anions, and the positive charge, your cations, which are your metals. So therefore, an ionic charge is between a nonmetal and a metal. A negative charge and a positive charge is what makes an ionic bond. And I'm going to go more into this. This really is an overview. Your covalent bond involves sharing of electrons, and I'll go into that a little more, and that is always between nonmetals only. So these guys will be chemically bonded with each other or itself, 2 oxygen atoms. That's a covalent bond. That involves sharing of electrons. All right. You can review this, properties of metals. You should know it, but you can read it. I want to stick with more of the bonding right now. But become familiar with the properties of metals and nonmetals. We went over a little bit before. All right, very important. The bond, I've talked before about the bond has energy. It's stored, is called potential energy. So that is this force here. Now this is the Coulomb's law, but we use a proportionality. So we'll just use the charge and radius parts of it. So I'm going to go to the whiteboard. And show you what those symbols mean. Because you're going to use it both this semester and next, particularly next semester, even more. So the force of a bond is equal to, we'll say a proportion, because I'm not going to use that constant. That constant, that K, lets you turn it all into a number. Proportionate means you're still getting the relationship. So it's the 2 charges. Q is charge. So if I have fluorine and let's see, sodium. Let's do chlorine. Chloride ion. You're familiar with sodium chloride. So if I have a sodium ion and a chloride ion, these 2 are going to form an ionic bond. The Q of the one is +1 and of the other one is a -1. Now these are absolute values, so you actually don't worry about the charge. If you look back at that equation, it's set up as an absolute value, which means we're not worried about the charge is strictly the number. Okay, so that's what the Q is. The Q is the charge. Whatever if it was magnesium, that would be 2 would be your charge. The bottom part is the radius squared. So this means as your charge gets bigger, your force is going to get bigger, right? The bigger your top number is, this is a fraction, the bigger your force is. So we say it is directly proportional. That little symbol means proportional to charge. As the charge goes up, your force goes up. The strength of the bond. But what about the R? R is radius. That's on the bottom. So as R goes up, since it's on the bottom, when you have a fraction, if I have a fraction of 3 over 1 versus 3 over 3, the bigger my bottom number is, the smaller my whole number is. So this equals 3 and this equals 1, right? Because the bigger that number is, the smaller my answer is, my whole number. The same thing goes here. The bigger my radius is, the smaller my force is. So if this is bigger, force is going to be smaller because it's making the bottom half of the fraction bigger. And so we say radius is inversely proportional to the force. Because the further you get from the nucleus, the bigger your atom is, the further away you are from the nucleus, that's where that positive center is, those positive charges. And the further away you get from that, the weaker the pull is. And your bond is forming between the electrons, which is your negative charge, and your protons in the center. So if they're further away, the pull of those protons is going to be less. So the bigger your radius is, the smaller your force is. Okay, going back to the slides. And if you remember from reading the periodic table, there was a trend. So let's go back up to the periodic table. No, that's not what I want to do. Got a mind of its own. As we go to the right, as we go across a period, if we go from lithium all the way to fluorine, your radius gets smaller because you're getting an increasing number of protons, and every time you add a proton, you're increasing the pull of the electrons around that nucleus. So you're getting smaller in this direction, but you're getting bigger as you go down because you have more and more shells. Every time you add a period, you add another shell of electrons. And so it's getting bigger and bigger. You get down to iodine is quite large. Fluorine is tiny. So because it has that many more shells or orbits full of electrons. So you use this relationship when you're looking at that equation. So if you're given two examples to compare and the sizes are equal, you're given a picture of two little ones, but the charges are different, then you're going to use the direct relationship with the charge to say, oh, one is stronger than the other. So just get a feel for that concept right now. Okay. So of course, when we're talking about charges, we're talking about ionic bonds. Up here. So ionic bonds are formed between a metal and a nonmetal, and yes, you definitely need to know that. It's an electrostatic interaction. The relationship is the positive and the negative of the ions are creating the attraction. Ions form, or ionic compounds form matrices. They do not exist as a single individual unit. It will always exist in a large crystal of lots of these ionic compounds in a very specific geometric relationship depending on the sizes of the atoms involved. So being sure you know that they always exist in a crystal or a matrix. They do not exist singly. Therefore, when we call a single compound, we call it a formula unit. So a single sodium chloride, because sodium chloride doesn't actually exist as a single sodium and a single chloride. We'll refer to it that way, but we call that a formula unit. It's a unit of a larger structure. That's what it actually exists in nature. Covalent bonds, on the other hand, has some very big differences. First of all, it's non-metal and non-metal. It is the sharing of electrons. These are not ions coming together. These are just regular elements coming together, and they complete the octet, the 8 filled shells, by sharing. So, and I'll go back to the board in just a minute. One of the big, very important things about a covalent molecule is you can have an individual molecule. If you go back and you remember that little video of a boy and his atom, those were individual carbon monoxide molecules. So you cannot have a single individual ionic compound, but you can, I often do, with covalent. Now, this is where we're going to start using our terminology a little more specifically. Yes, a molecule is 2 or more shared atoms chemically bonded. But because a molecule involves, generally, it's assumed that chemical interaction is covalent, we call covalently bound atoms molecules. Yes, they are compounds by definition because, for example, this one, carbon dioxide, it has different atoms. So it is a compound by that definition. But we don't call ionic combinations molecules because they really aren't sharing electrons. They're just hanging out next to each other because of that electrostatic interaction. So we call them compounds. And often when we talk about molecules, and as we go on in the course, we're going to be going into the equations, we will be talking, it's our shortcut for a covalent molecule, but you'll get used to that. So let's go back to the whiteboard just for a minute and let me show you about this sharing of electrons. We use fluorine. So if you remember, fluorine has 7 electrons, and the way we draw them is called a Lewis dot structure or Lewis structure. We'll be getting into this next week. We actually, remember, we'll draw in an orbit, and we draw the center, and then we draw the dots. There's 2, and then the second orbit, 1, 2, 3, 4, 5, 6, 7. It doesn't matter what you place where, as long as you write them down separately. Okay, you can't do that every time we're going to draw an element. So we do this simple, cool little shortcut. It's basically, we're taking that idea, but we're putting it around the element itself. So we place, and we just use the valence electrons, just the outer electrons that are the ones available for chemical reactivity. So there's my 1, 2. I know they're paired. Yes, normally you would actually go 1, 1, 1, 1. But since I just drew it, I know what it looks like. That's 1 fluorine atom. It has 7 electrons. It has 3 sets of paired and 1 lone. Okay, unless we have another fluorine atom over here too. These are not ions. They have not given up or taken any electrons. These are elements. Move you up here. We'll call his X's. So in covalent bond, they do not give up or take electrons, they share them. And the electrons will circulate in the space between the two fluorine atoms. Remember, you got your nucleus here with your protons. So the electrons actually are going to circulate around, and this field, this filling of the space, is your bond. And each fluorine now has 8 because of the sharing. So the sharing counts as a whole nother electron for each individual fluorine atom. So it has, this one has the one that it brought to the party, and then the one that is borrowing from that fluorine. And this fluorine has the one that it brought to the party, and then the one that it's borrowing and that is circulating around. So that counts as 8. So each one is now considered to have 8. And when we draw this, which you'll get into next week, what we do is we draw, you'll draw the fluorine, and you'll draw the fluorine, and you'll do the paired, but then the ones in between, you just draw one pair in between, and that indicates a bond. One of these electrons that is shared between them is from this fluorine, and one is from that fluorine. But if you count, I count 2, 4, 6, 8, 8 for that one. You count the same ones twice, 2, 4, 6, 8, because they are both feeling the full effects of all of those electrons. All right, so that is how a covalent bond gets its 8 electrons. It's octet. That's called an octet, 8. By borrowing, actually by sharing, because they're both sharing. And that, so what are the biggest differences between ionic bond and covalent bond? Sharing versus not sharing. So what's the attraction? One is, covalent is, you're actually sharing the electrons. It's ionic, it's electrostatic interaction. They're not sharing electrons. A covalent molecule can exist individually. Ionic will not. The ionic is considered a formula unit, and it actually only exists as part of a crystal. And the other is that an ionic bond is formed between a metal and a nonmetal, because you're going to have a positive charge with the metals and a negatively charged ion with a nonmetal. So that's why. Covalent is nonmetal and nonmetal. It does not involve ions. Okay, so know those differences. So this is another description of that, seeking that octet. All of your, just as the end goal for an individual atom is to reach this state, they can do that by sharing electrons with another element, and then to get the octet state. The octet rule is filling those valence shells with 8 electrons. So a little more about the ionic bond. So it's a bond, and it is a bond created by electrostatic attraction, the positive and the negative charges. So you already have ions existing, they come together because of that charge attraction. The space in that crystal, because it's a very specific, each one very specific spacing and geometric arrangement, is a balance, once again, between the attraction of the electrons or the charges with the opposite, but also repulsion of electrons to each other. Because remember, if your electrons get too close, you've got negative charge. Because even with your ion, your positive ion, there are still electrons further down in there, right? They're in the lower orbits. So if you get too close, they're going to start overlapping and you have repulsion. And then again, the nonmetal with nonmetal gives you covalent bonding. Once again, the length of that bond, you have the two atoms coming together. At that one point, they're going to hit the perfect point where, because as the electrons are circling and sharing, they're circling to get the attraction of the protons, right? So they're going proton on this side, protons on this side. So they're back and forth between the protons and the two nuclei. But if they get too close, there's a repulsion of the other electrons in the element. So you have that perfect balance between attraction and repulsion of the proton-electron attraction, electronic-electron repulsion. And that's what determines the bond length. And the bond length, they tend to be pretty specific. And we can look them up in tables and get their numbers. We have reasons to want to do that, but not this semester. All right, so the different types of bonding give you different properties, and you do want to know these. So ionic compounds will exist in a crystalline solid. They generally are solids, whereas molecules, here we go, molecular compounds. When you hear that, know that we're talking about a covalent. Can exist as a gas, a liquid, or a solid. Ionic compounds are very hard and brittle. Think about a crystal, right? It's hard and brittle. Whereas covalently bound molecules are more often softer, or they're a gas and a liquid. So if it's a solid, it's generally more of a soft solid. Ionic compounds have a very high melting point. You have to break through a lot of those bonds because it's in a crystal. It's not just one bond. You've got all those interacting ones to separate it, to change it from a solid to a liquid, or from a solid to a gas. And so therefore the melting points and boiling points take a lot of energy. They're very high. Whereas covalently bound molecules, they are lower. Again, high density for ionic, low density for molecules. Ionic compounds are very strong electrolytes, and when we get into solution chemistry, we're actually going to explore this, and then you will understand why. Molecular compounds, covalent bonds, or covalently bound molecules are weak electrolytes or even non-electrolyte. Electrolyte means it carries a charge when you dissolved it in water, because now you have charged ions dissociate and they're traveling in the water. So electrolyte means it carries a charge. It'll carry a current. If you have Gatorade is an electrolyte, salt water is an electrolyte. So if you have an electrolyte in water and you put a current in there and you stick your finger in, you're going to get zapped if it's ionic, not necessarily if it's molecular, because that doesn't carry the charge. And electrical conductivity, same kind of thing, is good when you melt your solid, whereas not so much with the molecule. So know the differences between your ionic compounds and your molecular. So this is the same diagram, but now there's an addition to it, using the specific language that I was talking about. So here we have the elements, and an element can either be paired or a single. This element actually should be up here. And so we have an overlap between an element and a molecule, because a molecule is two or more chemically connected. And under molecules, we do have the subset of a covalent compound, or rather of a compound. And so now we've taken compound though, and we've enlarged it, because a compound can be covalent. The definition is two or more different atoms chemically bonded. So that is a subset of a molecule. But over here, in its outside of the molecule terminology, we have the ionic compound. That's a very specific definition that we use when we talk about ionically bonded elements or atoms or ions. We call them ionic compounds. So a covalent, yes, it can be a compound or an element, but we generally call them molecules. But ionic is always called compound. This is just something cute. I'll let you read it to kind of talk about the differences between the two types. So take your time, pause, read, enjoy. All right, so if we look at these, I'm going to minimize this so I can bounce. Yeah, great. So carbon tetrachloride, that's carbon and 4 chlorines. So is that ionic or covalent? Well, the very first thing you do is you go to the periodic table and you say, are they metals or nonmetals? Carbon is here, that's a nonmetal. Chlorine is here, that's a nonmetal. You have 2 nonmetal elements bonded together, therefore it is covalent, or remember, molecular. That's our language now that we're using. So that one is molecular or covalent. Calcium fluoride, if you go pull up a periodic table, you will see that calcium is a metal, right? Let's go look at it again real quick. Come on. Calcium is here, group 2. And fluorine, which was the other part of that, is over here. So you have a non-metal fluorine and a metal. Therefore, that's ionic. That's what you look up to determine if something is ionic or covalent. So that's your test. Metal and non-metal, or non-metal and non-metal. So the third example, you have a sulfur and fluoride. Those are both nonmetals. H2O, remember, we're treating hydrogen as a nonmetal, even though it's on the left side. That's only because it has one proton. But it behaves as a nonmetal, so we treat it like a nonmetal, so this is covalent. Now we have copper, Cu is copper, and this is called carbonate. So this is a little bit trickier, and I'm going to get into that next section because this is actually ionic. Copper is a metal, so that right there would tell you it's ionic, because as soon as you have a metal, you have an ionic compound. But the carbonate, the carbon and the oxygens, that is they're actually covalently bonded to each other in what's called a polyatomic ion. So I'm going to go to those next. And then go over this slide. The answers are there, pale yellow, but try to answer it without looking at answer it yourself without looking at the pale yellow. Okay, I'm going to stop here. So this is the end of part 1, lecture 5, and the next section will start going into chemical formulas.